So, morning everyone, welcome back. Hope you had a nice rest. So we are about to begin today's that is going to be shorter and more smooth. So we have the pleasure of continuing with this special talk celebrating the 42 years and perspective and experience of Jorge Vázquez, who has recently retired, but he wills to continue working with us. Indeed, he will still support Daniele and me in the task team, so he will still be involved in a way with Greece. So yeah, he will still be a science team member too. So let's welcome him and let's listen to all his experience. So I hope you enjoyed the talk. Jorge, welcome. Okay, you can stay here. There,
Thank you so much. And thank you also for the opportunity to give this talk. It's been 42 years and it's been amazing. Gris has such an influence, I think, on everything, not just on SST. Next. So it's been a long time when this is a picture and I still have a little bit of hair left on my head. So next. Oh, it looks like it's almost at a meeting in Biarritz, so it might have been like 2003 or 4. So yeah, it's been a while. Oh, next slide. Thank you. So in terms of, I'll have to go through this quickly. The web story has all of the details of, on our page. Thanks to Christina and all the support. So my first experience with GHRSST was at to the very beginning of the project, which is where GHRSST27. The first meeting was actually held in Ispra, Italy. And although it was an initial meeting, one of the things that immediately impressed me was the fact that this was an international effort. That might sound trivial right now because this is where, the world has changed, yes. But at that time, this was a very, very big thing. The international aspect of GHRSST, the international collaboration with respect to data distribution and everything else, that was a very impressive part from the very beginning. Next slide. So the second strong focus, I think, was, with respect to GHRSST was, in a sense, not just on the focus of the application of SST data sets from a scientific perspective, but also the operationalization of those data sets in near real time. This was a huge, I think, part of GHRSST from the very beginning. And this also led to the infrastructure of what we call the regional data assembly centers, the global data assembly center. So again, this sounds trivial, but this was a huge part that set GHRSST up from the very beginning. Next. So what in terms of building the GHRSST data infrastructure, and this was also, I think, amazing. I was the project scientist for the PRODAC, during these beginning days of GHRSST. So the focus was on this concept of having one global data assembly center, which was literally the data distribution point of GHRSST. And Armstrong was involved heavily at that time also. And also the regional data assembly centers, which was going to be the data centers where the actual data was provided from and produced. So this was, again, it sounds like what's the big deal? But this was huge at that time, and also in terms of supporting the open science. And I want to say very, very clearly, because today we use the word open science as if it's something new. Everybody in this room and everybody involved from GHRSST from the very beginning should be very, very proud of the fact that the concept of open science was part of GHRSST from the very, very beginning. And that was also, I think, huge. And that was part of the whole issue of the data infrastructure and how it was set up within these regional data assembly centers and the global data assembly center which was actually located where at the physical oceanography distributive active data center, the PODAC at JPL and NASA. Next. Oh, and this was just one of my favorite pictures of a meeting that we had at JPL, yes, discussing the PODAC and the GDAC and GHRSST in general. So next. So a major step forward again, and I mentioned this, was the concept of open science. And what did this mean? It meant that the data, for example, and things were no different back then. There were still multiple SST data sets that were available, and that's why we had so many multiple, regional data assembly centers. But all of the data again came into the global, this sounds like a trivial thing, but again, it was not, came into the global data assembly center. People had one place they could go to, to actually get SST data and the information they needed. That was again a huge concept for open science. And of course, this also contributed significantly to the concept because NASA had the concept of open science even back then too. Science, the data should be available freely to anybody that wanted to use it around the world, from both from an application perspective and also from the perspective of operationalization. So this, again, from the very beginning of GHRSST was huge and in support of open science. And I also just want to say that that was also a time when I think worked very closely. Ed Armstrong was involved in all of the leadership also in terms of the open science of the data distribution and the GHRSST infrastructure, and also John Francois. These were amazing times. Again, international effort. Next. Okay, one of the things that one of the details in terms of how and the important discussions that were had at some of these very beginning meetings was what's going to be the data format? We have all of these different data sets. Are they all going to be in different formats? Well, and this is where the leadership of Craig Donlin and how he pointed us in the right direction was just so amazing in some of those original meetings. So yes, there was a lot of discussion as what is going to be the common data format. Today, it seems like that's a trivial question. Back then, it was not. And the decisions were made net CDF. That was a huge decision, that all of the GHRSST data sets are going to be in this one common format, net CDF. And not only were they going to be in the one common format, but they were also going to be within a data specification guideline called the GHRSST data specification document. So this also led to the operationalization of the data. It was an amazing effort under the leadership also of Craig and others. And so you didn't have to write 500 different pieces of code to read all of the data. You had one, and you could read all of the data sets. This was a huge step forward in terms of open science also. Next. Okay, I was just already mentioning this in terms of the issue of, and the meeting in Exeter historically was huge, and that was the one that was Craig Donlin, and that led us in the right direction. We also had a meeting in Pasadena where there was huge discussions, again, on data format issues. Next. The multi-scale, this is something that also we've been involved with that, from the very was, the issue of high resolution. Mike Chen, who was a principal investigator of the Mirror project, and also Ed and I were also involved in that project, I think was also a step forward in highlighting high resolution and applications to coastal areas and also regional areas, and the issue of gradients too. So that was also a big part of what we were involved with at JPL at that time. Next. So the focus on high resolution obviously is still a huge issue today. So again, GHRSST again set a standard at a very early point, and we're continuing now with that to move to the next steps in terms of high resolution and applications. But again, the Mur SST data, I think was also a breakthrough in moving forward with that and the focus on high resolution. Next. I also just want to mention quickly, because I think this was also a huge part of GHRSST and said was the issue of the Pathfinder Sea Surface Temperature Project, which is a collaboration between NOAA and NASA. And I also want to credit Rosanna Sumagaisai, because that was also a collaboration between University of Miami and the Goddard Space Flight Center, Jane Feldman, Peter Burnett. Again, this was also a huge collaboration, but again, focusing on the same issues of common data format. And remember now, the OISST, the Pathfinder, is the longest climate data record derived from satellites. It started back then, and GHRSST was a very important part of that. Next. So again, the Pathfinder Sea Surface Temperature, that was a huge project from the very beginning, and I'll just show you and one of the reasons that I'm sorry, I kind of focus on this too, because it was part of my research at that point, and I'll show you next. The Gulf Stream. This seems like, okay, we've all seen this picture before. Remember, this was this was totally new with respect to when SST came out in high resolution. I mean, my gosh, you can even see eddies on this at places. You could even see the frontal structures of the Gulf Stream. Major breakthrough with respect to GHRSST. Next. Again, and I also want to, I'm sorry, I just want to mention quickly also, one of the issues that was huge with respect to GHRSST, obviously you had these long data records, the issue of subsetting, because people wanted to work with the data in certain regions. High resolution, they didn't want to have to extract data over the entire globe. They wanted to focus in on a certain region. OpenDAP by Peter Cornell at the University of Rhode Island was huge. And also allowing, this issue of data accessibility, that was part of GHRSST. The other person, I'm sorry, I get a little bit emotional, was Rob Raskin at JPL, who first initiated this whole concept of data accessibility and visualization with the POET project. That was huge. That was a huge breakthrough also. OpenDAP came after that. But again, GHRSST was at the forefront of these issues of data accessibility. This was huge, guys, and this is something that this group and GHRSST should be very, very proud of, because this was also part of open science. Next. And just in terms of, I think one of the big things not to forget is the international aspect of GHRSST. I remember the meeting in Lima, Peru, where we had it at the Institute of Marine Science, and Lima opened up doors for international collaboration also with Latin America, and I was just so happy, because of that. So again, GHRSST was also at the forefront of a lot of these international issues of collaboration also. And that's something I think that all of us should be extremely proud of. Next. And I just want to mention quickly, this is a huge project also in terms of the international collaboration. Joseph Pasquale, who was responsible for having, I think, one of the longest in situ data sets off the Mediterranean coast. And this was, I think, a breakthrough paper, and myself and Mike Chin were involved in that, along with Jordi Salat. And again, this is an issue of SSTs, one of the longest climate, it is the longest climate data record derived from satellites. So the paper that we did, we compared trends from Mur SST and also the in situ data at that point, and found that the trends are very similar between Mur and SST. But this is also an example where I think also GHRSST has been at the forefront this was an example of how the incorporation of in situ data is so critical. GRIS was at the forefront of that, and also sail drone, I think with respect to validation of SST gradients has been huge. Next. Yeah, and the issue next, we'll just go through this quickly. This is just an example of the high resolution and the importance, off the California coast with respect to gradients. Next. Yeah, again, some of the GRIS milestones, I think I'll just, again, the infrastructure, the open science, the accessibility issue were all huge. The operationalization of the data. Next. Okay, looking ahead, next, what did I just, again, the GRIS community, the international aspect. Next. And I just want to show you, these are students that I'm working with at the University of Washington at the Advanced Physics Lab, and she sent me this 2 slides of Veer's data in the Arctic. And you can see I was just so excited when I saw them in terms of the future applications. You see the higher resolution in the Veer's data. This is off of the Alaskan coast. And I'll just leave with this as, I think, an issue for the future, high latitudes and high resolution. Thank you so much.
So thank you, Jorge, for this magnific review. No, don't go. Stay here with me. So this is a small souvenir from your stay in Japan. Come here with me, please. Here. And yeah, wait. So this is for, you remember your GRIS meeting in Japan. This is from GPO on behalf of all the GRIS community. Just a small, a small present, okay? Okay, so the show must go on. I'm going to ask all the presenters of the second session of the poster. Well, we have the poster pitch now that we proceed as on Monday. You just please line up here or there. Maybe it's easier here. We just listen this way, okay? Just in order, if you remember your number. Okay. Is it? He just learned Japanese. So are we ready? Not yet. So yeah, that's you. I was looking for you. Okay, thank you. Take that one.
Morning, everyone. My name is Haifeng Zhang from Australian Bureau of Meteorology. So in this study, we are evaluating 5 satellite-based LC heat flux products over the Southern Ocean for 2 decades. And to do that, we have collected as much as possible high quality, high resolution, typically 1 minute, in situ LC heat flux observations from exclusively research vessels and moorings. And as a result, we have a winner from those 5 products. So if you are interested in which product wins, or if you are interested in LC heat flux, in situ observations, or if you want to hear my seasick days, just come have a chat. Thanks.
Morning. My name is Haru Fujimoto from Japan. We are actually, making a wave-driven wave-driven upwelling pumps, and our focus is cooling water to a surface and cool the sea surface without increasing ecological risks. And the main result is that about 5 meter appears to be the safest and most effective cooling depth in Ise Bay, which is near Nagoya. Water at the depth is cooler than the surface, still has a sufficient dissolved oxygen, and also shows relatively high biological productivity. So my key message is not cold water is beneficial for climate adaptation and adequate risk reduction. Artificial upwellings should target a healthy cooling water layer, not simply the coldest water. Please visit my poster if you are interested in coastal SST cooling, marine heat wave adaptation, or safe artificial upwelling. Thank you very much.
Hello, I am Etaro Nakada from Hokkaido University. We compared 6 SST products with in-situ observations under tropical cyclone conditions and found significant differences in their bias patterns and temporal evolution. This figure shows the temporal evolution of the biases relative to the day of tropical cyclone passage. And especially 1 day after the cyclone passage, the biases range from 0.2 kelvins to minus 0.5 kelvins, depending on the product. So if you're interested in our poster, so I'd be happy to discuss this in more detail. Thank you.
Good morning. I'm Neeraj. So this is a poster by one of my colleagues, Jashad, who basically worked on the bulk skin SST differences and the conditions that modulate these differences in the Arabian Sea and in the Bay of Bengal. So here he used cruise data, and then he also used the ERA5 reanalysis data sets and found some interesting results. So please visit his poster. Thank you.
Hi, my name's John Mittaz from University of Reading, and we've been looking at whether or not it's possible to use the 3.7 micron channel on SLSTR in the daytime, which, as many of you will know, normally that is not done because the 3.7 micron channel is sensitive to solar radiation. So we've been looking at how we can possibly try to improve the daytime nadir SLSTR SST retrieval by using the 3.7 micron channel. So just come along and talk to me about how we did. Thank you.
Oh, okay. It's a shame because there was nice animation and things on the slide I presented. Anyway, this is kind of an update on the Darnall warming model that I presented in Montreal. We had this figure here shows on the left-hand side. This is the stuff we presented before, which showed the importance of including solar zenith angle and water vapor in terms of the insolation. But there were some issues, and the issues are represented here in this very small plot here. But if you go to the poster, it'll be a little bit easier to see. And you can see this kind of bulge there, which is basically a kink in the profile. We have fixed that kink now, and that's it for the whole for a range of solar zenith angles. And so that has changed the warming pattern, and you can see the plot on the right-hand side here shows the increase in warming you get when you use the new insolation scheme. And if you want to know more, come and see me at the poster or coffee break.
Thank you. Hi, everyone. I'm Shaquila, and I just want to say, Jorge, I do remember giving you all of that reprocessed Pathfinder SST data from the University of Rhode Island, working here during your days. I am going to talk about on this poster, essentially, the NOAA SSTs, reminding our agency that our SSTs are with our GHRSST processing, our GHRSST metadata, and various important components of GHRSST. And this work is to also illustrate that we have multiple levels of products that are important. And our National Weather Center, which we have to emphasize these days, given our current circumstances, does use these data. So to emphasize the products that our National Weather Center are using, and then to add, in addition to that, some monitoring parameters for the matchups, file counts to maintain a consistent SST product. We will have the blended SST going to the National Weather Service. They have long-term used our OISST, and some of them have moved away from that, and they're very frustrated. So they're looking to have a more consistently processed, gap-free data set. So they are currently investigating using our blended SST, and so I'm working with them on getting that into our weather service system. Thank you.
Okay, so this is a complement to the first poster of the week and the presentation of Emmanuel yesterday about the Calista project. So in order to support the development and the assessment of the algorithms and datasets that have been presented yesterday, and most of all the usage for application, so we have developed this Jupyter-based virtual research environment. It's hosted on Ifremer supercomputer and available accessible on demand. And it hosts all the EcoStress and Landsat 9 archives that we have collected and processed, and all the resources and data that we have produced for the assessment of the algorithms. It comes with some environments prepared, like Conda environments or Dockers for some software like RTTOV, and services for data selection and visualization, documentation, some tutorials and notebooks to help you start with a different data set. So it's meant to be like a remote collaborative environment.
I again am not Oli, but Oli sends his work. Advanced Clear Sky Processor for Oceans is what AXPO stands for. So there was a comment the other day about it's not a cloud mask. You're looking for the clear skies. I think that's just reiterated. It's interesting to think it like that. The new version, so the AXPO is the NOAA's level 2 and level 3 data and used in many downstream products and applications. Oli worked on a version 3.10, which includes feed-forward neural network that improves nonlinearity in the handling nonlinearity in the BTs, view angles, water vapor aerosols. It also has a new landmask, and it pulls forward clear sky masking that we have in some version 3.0 products. With 3.1, all of the sensors will come up to speed, and then we will sort of deliver that to operations and then initiate reprocessing. So stop by and see the results here with the from the new processing. Thanks.
Hey, hello everybody. It's Ed Armstrong here. My poster is on this popular mirror data set that Jorge mentioned in his talk, and that we've already seen some representation of used in scientific studies, such as the hotspot evaluation of the coast of Antarctica. So mirror, yes, is one of the best contributions of level 4 data sets from NASA to GHRSST, and we'd like to keep it going. Fortunately, there's been a lot of pressures within NASA to maintain these processing systems. So about a year ago, I received a small grant to refactor and migrate the mirror production system into the cloud. It was a 1-year open source, high-priority open source science proposal that was awarded to me and my team. And so this is where we've taken it so far. Essentially, what we wanted to do was to modularize and Dockerize the system in preparation for migrating and running the mirror processing system in the cloud. We call it actually the Mirror in the Cloud project for short. And we solved a number of technical difficulties. Mirror is a very complex processing system that contains both MATLAB, Python, and executable Fortran code. So we were able to successfully resolve a number of technical challenges to modularize and Dockerize and actually run MATLAB code in the cloud with a precompiled license. And so, yeah, come by and talk to me if you're interested in this processing system we developed and how we did it. We intend to make this eventually an open source software, so it'll be open and accessible to the user community to be able to be adaptable, to use it if you want to, or contribute to improvements to it. And really, we're getting ourselves ready to run in the cloud to ensure that we have the scalability necessary for things like reprocessing campaigns, and also getting ready for the era when we don't have MODIS and we start integrating other sensors like VIIRS and the next generation AMSR 3, et cetera. So stop on by and I'll tell you a little bit about what we've done so far. Thank you.
Okay, hi, I'm Claudia Fanelli, and at CNR in Naples, in collaboration with the University of Naples, we are working on a machine learning-based algorithm to, let's say, interpolate SST data from the L3 level to the L4. We are doing that combining a convolutional LSTM with a unit that exploits spatiotemporal context from 15-day sequences to reconstruct the gap-free daily SST. So if you're interested in what we are doing and how we are doing it, stop by to my poster. Thank you.
So hi, so this is work I did with the help of my students, wherein the challenge was to construct a high resolution sea surface temperature using microwave data. See, IR is contaminated with clouds, but we do have the microwave data on those regions. So, but however, the resolution is not very high and the gradients are not quite good represented in that data. So by making use of enhanced super resolution generative adversarial network. So we were able to get high resolution SST using the microwave SST as an input. So we used around 20 years of data to do the training between the microwave and the IR patches, which were cloud-free, and you could get some interesting results. Please do visit the poster. Thank you.
Welcome to session 4. Hello, welcome to session 4, climate change variability and application in global and regional sea and sea ice surface temperature. So our first speaker today is Pia. So what do you?
Thank you very much. And I should say that this work is done in collaboration with many colleagues from DMI. And first, I'm going to give you a brief introduction to why I think this is really important. As you're probably all aware of, climate changes are most pronounced in the Arctic, which is evident through widespread changes in the snow cover, sea ice cover, permafrost, and land ice, and not at least a warming rate much higher than the rest of the world. However, despite much attention, there has actually been limited consensus on the magnitude of the warming rate over time. In 2016, most research shows that the Arctic is warming about twice as fast as the global average. A few years later, the IPCC report states that it has warmed more than twice the global rate. And later the same year, the Arctic Council affirms that the Arctic is warming at 3 times the global rate. And the latest scientific results show that the Arctic has warmed nearly 4 times faster than the globe. So even today, there are large differences and uncertainties in the Arctic surface temperature estimates and limited consensus on the magnitude of Arctic amplification among the different models, reanalyses, and observations. And that's what you can see from the figure here, which is from the latest publication from Rantanen et al. And this really highlights that there still is a need for more consistent and accurate surface temperature estimates to improve the monitoring of the Arctic region. And that's the region that has received the most attention. So the same applies for the Antarctic region, and I'll come back to that. And at DMI, we have recently developed the first global combined gap-free sea and sea ice surface temperature record. Joanna mentioned it Monday too. It's developed in C3S, and it goes back to 1982. And it's based on the ESA CCI version 3 SST data and the ASTI IST data over the sea ice. And these input satellite observations, they are first aggregated to level 3S fields, and then they are run through an optimal interpolation scheme to provide the daily gap-free fields and uncertainties, as you can see on the right. And as Joanna said, the data is now available in the climate data store, and I'm not going to talk more about the methods or validation results here. So if you are more interested in that, you can see the publications in the bottom here. It's in preprint. And this data set that opens up for a number of new opportunities to investigate and assess key questions, and I have listed 4 here that I'm going to talk about today. The first one is that now we can actually compare the surface temperature trends from using the traditional under ice surface temperatures with the sea ice surface temperatures. And then we can assess whether the warming rates they have accelerated. So what you saw in the first slide, is that an indication of our accelerating warming rate in the Arctic, or is it just improved estimates of the warming rate over time? And then we can look at if the extremes, they are becoming more frequent in the polar regions. And also we are going to look at whether the Arctic warming is still underestimated today. So I'll start with the first one. And these figures here, they show the warming trend using the traditional under ice surface temperatures in the left panel and using the sea ice surface temperatures in the right panel. And as you can see in the left panel, the sea ice regions appear as no trend areas. That's because we're using the under ice surface temperatures. And that's insensitive to the changes at the sea ice surface temperature, as you know, which means that it's not a good indicator of climate changes in polar regions. And despite of this, it has been widely used in the C3S indicators, in the Ocean State Report, and also in the IPCC, which are referring to an Arctic SST estimate, just averaging the top of that figure. But if we look at the Arctic region, we can see that there are actually trends of 2.5 degrees per decade that are missed in the under ice SST. So that's more than 10 degrees of warming over this period that we can see now. And that is important for the global surface temperature estimates as well. It's actually resulting in a 43 increase in the global surface temperature trend. And that's what you can see from the top panel and the left histogram, where we have compared the SST under ice SST trend together with the 60 north, 60 south trend and our SST trend. And the largest differences, those are seen in the Arctic, as you can see here. And for the Antarctic, we actually see reversing of the trends, going from a slight negative trend to a slight positive trend. And we find that the global combined sea and sea ice surface temperatures, they have increased with 0.75 degrees. And the Arctic has increased almost 6 times the global SST-IST trend. So now I'm going to look at how the warming rates have evolved over time. And I'm doing that by plotting the trends using different temporal windows for different years. So the top of the triangle, that's the trend for considering all the 40 years, the full climate record that we have. And then in the bottom, you have a sliding window of 10 years and from different central years in the bottom here. And be aware that the color bars or the scales of the color bars that differs among the different figures. We have the global to the left and then the Arctic and the Antarctic. And it's clear that we have these very strong polar contrasts. The Arctic shows warming throughout the entire record. And we can see that we don't see an acceleration in the warming trend from this figure here. We have a peak warming around 2002, 2003, having that as a central year. And that's actually the case independent of the length period that we're considering. For the Antarctic period, the trend has first been cooling, then warming and cooling, and now warming again. And that seems to impact the entire climate data record. So what's happening in these recent years in the Antarctic? We can have a closer look at that. And here I've ranked the annual anomalies from the warmest in the top to the coldest in the bottom. And the Arctic, that's the orange one, and the Antarctic is the purple one. But if we start looking at the Arctic, we can see, if you can see, yeah, some of you can see that the earlier years, they are ranked as cold years for the Arctic. That's what we typically see. And we have late warm years ranked here in the top. And all of the 10 warmest years, they are occurring since 2007. For the Antarctic, the picture is a bit different. Here we have some late cold years here in the bottom, and we have early, relatively warm years. But then we see a shift from this random clustering of a random ranking of warm and cold years to a clustering of recent very warm years from 16 to 24. They are all located here. So that's what we see. And we can also see from the figure that 24 is ranked as a combined Arctic and Arctic top ranking. So let's take a closer look at that. This shows the daily anomalies for the Arctic and Antarctic region. And for the Arctic, we can see that almost all days of 24, they were warmer than the climatology. And the same is the case for the Antarctic region, except from the last 2 months. And then the third question is whether the temperature extremes are becoming more frequent. Now we have looked at daily and monthly anomalies, but in order to look at local extreme events, we have tried to apply the marine heatwave framework to this combined SST and IST dataset to capture what's going on top of the ice as well. No need to go into the definitions. I guess we heard enough about that yesterday. So here's how it looks. The figures here, the maps, they are showing the AMAT region. We use this as input for the AMAP report. And in the top figure, you can see the maximum heat wave category that was observed during 2025. And you can see that 96% of the region experienced a heat wave in 25. And in particular, you can see that over the sea ice, the central part of the Arctic sea ice, that region experienced a marine heat wave of category 3. So this is something that we wouldn't be able to see if we use the under ice SST. For the cold spells, they are less frequent, as you can see in the map below. And the figures, or the graphs to the left, they shows the percentage of the surface covered with cold spells and marine heat waves over time. And we can see, as we probably also expected, from this setup, whether we have an increase in the Arctic marine heat waves over time and a decrease of the cold spells. So this is something that we're going to look more into, and we have also done the same for the Antarctic region. And here we don't see the same clear pattern over time. We see more frequent heat waves in the beginning of the record and again in the end of the record. And for the cold spells, it's more or less the same throughout the entire record, maybe a slight decline towards the end of the record. And we see that we had in 25 marine heat waves occurring over most of the region again, but we also see a lot of cold spells occurring in 25. So this really highlights the large variability that we see in the Antarctic region. So I'm moving on to the final question. Is the Arctic warming still underestimated today? Now we have improved information, we believe, over the sea ice to look into that. And we have looked at that already previously using our Arctic reanalysis product from CE. And that is published in the top one of the publications. And in that paper, we use satellite-derived 2-meter temperatures to benchmark SIMX and the R5. And you can see that, I mean, the 2-meter temperatures, that are those from, we derived in the Eustace product. The reference for those are in the bottom. That's using the simple regression model to derive 2-meter temperatures. And you can see an example of these 2 air temperatures in this map here. And then we have the difference from AR5 and the difference for SIMX6. And you can see, which was well known, that AR5 has a warm bias over the Arctic sea ice. But what was probably not as well known was that the CIMIP models turned out to agree quite well with the satellite observations over the central part of the sea ice. In the same paper, we also looked at how the trends compare over time. We have the surface temperature trend in our satellite observations here in the purple. And then we have the difference of the trends from ER5 and CMIP6. And we found that both ER5 and CMIP6, they underestimate the warming trend compared to the satellite observations. ER5 to a larger degree than CMIP6. So this is something that we look more into, and we also looked at whether we can actually trust our satellite data or the trend in that. And the argument or the reason that we believe we can do so, that's because we have validated both our satellite record, but also ER5 against in situ observations. And it's mainly the top plot that you should focus on. It shows the median difference from the ER5 to the in situ observations, different sources of in situ observations in different colors over time. And the same for our satellite record here in the bottom. And you see that we have a cold bias, or no, maybe not a bias, but we are colder in the satellite observations than in situ observations. And part of that is namely because of the skin versus 2 meter air temperatures. And for the ER5, we see that we are generally warmer than in situ observations, but we also see that the warm bias in ER5, that's decreasing over time, meaning that ER5 gets colder and colder compared to the in situ observations, while the satellite observations are constant over time. So this indicates that ER5 is underestimating the warming, not only against the satellite observations, but also against the in situ data record that we have. So the next steps, that is to use the improved 2 meter air temperature estimates that I mentioned for the task team reporting Monday, where we use machine learning methods to derive 2 meter air temperatures. And then we're going to expand to other observational data sets and maybe other reanalyses. I've shown here an example of the warming trends from our satellite observations, ER5, and now also with Berkeley Earth for 2 meter air temperatures. And since we now have the global data set, we can also have a look at the Antarctic region, and that's what's shown in the bottom. And here, it actually also indicates that the warming trend might be slightly underestimated in ER5 and Berkeley Earth. But this is something that we'll look more into. But these results or initial findings, they indicate that we can use the global SST and IST data to get an indication of how well the Arctic amplification and global warming is estimated. And we have also taken a look at the Arctic amplification using our data. And in order to do so, we have populated our land surface temperatures with ER5 in this case, so that it enables us to estimate the Arctic amplification in each point. And that's what's shown here. So it's a local Arctic amplification ratio, if you can say so. And here you can see that there's also large differences from C3S, which is our sea and sea ice surface temperatures populated with ER5 land temperatures versus the ER5. So these differences, they are only because of the differences over the ocean and sea ice. And if we consider the total Arctic amplification, it goes from 3.4 in ER5 to 4.4 if we use our sea and sea ice surface temperatures. So it actually indicates that there's still an underestimating of the warming in ER5 and maybe in more data sets. We're going to look at that. So this is my last slide with the key takeaway messages for each of the questions that I have assessed here. And for the first one, we found that including ice surface temperatures, it impacts the global surface temperature trends by around 40% compared to using the SST and non-ice SST. And the largest differences are as expected in the Arctic, and we see these reversing trends for the Antarctic region. And the next question is whether we are seeing an accelerating warming or not. That was mainly focusing on the Arctic because we saw this increase in the Arctic amplification estimates over time. But that's not what we see. We see a persistent warming, but with a peak warming around 2002 and 2003. And for the Antarctic, we see a much weaker warming trend, but a clustering of recent warm years, which really highlights the importance of keep monitoring the Antarctic region in these years. And then are the temperature extremes becoming more frequent? Yes, in the Arctic, we see an increase in the marine heat waves, but we see a decrease in cold spells. For Antarctic, we had most of the marine heat waves occurring in the beginning and in the end of the record, and we saw this very large variability. And we did capture marine heat waves over the sea ice, which would be missed in the SST under ice SST calculations. And finally, the last question, is the Arctic warming underestimated? Yes, that's what we see, at least compared with our satellite data and with the in situ observations that we have. It is underestimated in AFI and maybe also in Berkeley Earth. And we find that the Arctic amplification that increases from 3.4 to 4.4 just by including the information we have over the sea ice regions. But we need to look more into this. That's all I had. Thank you.
Thank you, Pia. We will take questions at the end of the session. So our next speaker is Claudia. She's going to tell us about water spouts in Mediterranean Sea.
Hi again. I'm Claudia Fanelli. I'm going to give this talk on behalf of Elenia Voglio that couldn't be here, which is my colleague working at the Institute of Atmospheric Sciences and Climate. And this work has been made in collaboration with two colleagues from there, Elena Voglio and Marcello Miglietta, and in collaboration also with Andrea Pisano that you all know. So today I'm going to briefly talk about ocean atmospheres, drivers of Mediterranean waterspouts. Just to begin, I don't know if everyone knows what a waterspout is. They are small-scale vortices forming over water, and they are typically associated with convective clouds. They are very similar to tornado, but they develop in different environments and through different mechanisms. And even if they last about 10, 20 minutes, they can have very severe consequences. So far, we decided to carry out a new study over the whole Mediterranean Sea, since so far the existing study was, they have a sub-regional focus and they take into account very small time series. Also, they tend to study ocean and atmosphere in a very separate ways, but observational and numerical studies shows that one of the main trigger of the waterspouts is the strong temperature difference between the sea surface and the low troposphere. So we think that this is something that has to be studied jointly. So we selected over 3,500 events from the European Severe Weather Database. I have to say that this database is composed by events that are reported by someone. So someone has to physically be there, see the waterspouts, take a photo or a video, and then it goes into this database. So you will see that this is a little bit a problem for, you know, the strongness of the statistics. We selected only the highest quality events from 2008 to 2024 over the whole Mediterranean Sea. For the ocean part, we used the SST multi-year product that we at CNR are producing for the Copernicus Marine Service, while for the atmospheric variables, we are using the ERA 5 reanalysis. So as you can see, we decided to start our series from 2008, since, as I was saying, the methodology that allowed an event to be on the data set is very clear that before the 2008, we weren't with our phone on our hands all the time, so there are very few events reported. We found out that we have a diurnal peak between 8 and 11, but again, this can be biased by the fact that during the night there are not so many people around to see the waterspouts. We studied the whole Mediterranean, but we also divided it into 3 sub-regions, and we found out that the central Mediterranean is the region with the highest peak. And the season when we have the higher number of events is the autumn, with September being the monthly peak. So from an atmospheric point of view, we found out that waterspouts develop under moderately unstable environment, so we don't have extreme single values. You can see on the right the composite anomaly maps calculated only on the days where we have a waterspout event. As we expected, we have a negative anomaly of the geopotential and of the mean sea level pressure, and also a negative anomaly of the temperature at 850 hectopascal. But it's interesting to notice that actually the waterspout events, they don't occur on the core of the negative anomaly of the temperature, but on the eastern border. And we think it's probably because it's very important, actually, the front of the temperature. So the gradients are the ones that are actually producing the instability. We also find a positive anomaly, of course, of the Cape. We know that waterspouts occur on cyclonic environment, and this is confirmed by the bulk wind shear anomaly and the wind at 850 hectopascal. And finally, we found a negative anomaly of both the sensible and latent heat flux, where the latent is dominant, which means simply that there is an upward transfer of energy from the sea to the atmosphere. From a sea surface temperature point of view, we found out that there is a strong seasonal signal, with summer event, of course, occurring over the warmest water, and winter and spring over the coolers. There is no a spatial difference among the basins, both for the SST on the top and for the SST anomaly on the bottom. So the seasonal variability is actually much stronger than the spatial variability. Again, autumn is the season with the highest waterspout frequencies, where the waters are still pretty warm. And waterspouts preferentially develop over slightly warmer than normal water. So extreme anomalies occur, but they are uncommon. You can see here the mean SST anomaly map calculated only on the days of the waterspouts events. And for the 3 regions, we always have a positive anomaly, even if it's not extreme. And the time series can show you that extreme values are present. It can show that we have a clear increasing of the SST anomalies, especially over the last decades. But I have to say that negative anomalies are still observed, especially in spring and in the summer. This is probably because in summer, the temperature of the water is already high enough to trigger the instability. While in spring probably is because we have a strong contrast due to the cold outbreaks in the atmosphere. Here, just to show the correlation between the SST and the Cape on the left, and the SST and the temperature at 850 hectopascal. We have a moderate positive correlation between SST and CAPE. Of course, we know the warmer sea surface conditions tend to be associated with enhanced convective stability through surface heat and moisture fluxes. But the very strong correlation between SST and the temperature at that high is not so trivial, because large-scale atmospheric processes are really important. We also had a look into the three most famous, probably, indices. So the Western Mediterranean Oscillation Index, which is between the south of Spain and the north of Italy. We found out that we have a positive phase in the central and in the Western Mediterranean Sea, while we have a reverse sign in the Eastern Med, but is where the index is less representative. The Mediterranean Oscillations Index is coherent with the first one. We have negative values on the west and positive values on the Eastern Med, while the now doesn't show really any, let's say, any really strong indicator, because it has a near neutral mean phase during waterspout days. What was more interesting is this index, the Szilágyi Waterspout Index. So this has been invented for the North American Great Lakes. It compares the difference on the x-axis between the sea temperature and the high temperature at 850. While on the y-axis, we have the convective cloud depth. So all the water pouts should fall into the region between this index being equal to 0 and to 10. But when we apply this index at our data set, we found out that only the 75% of our events were falling there. So being the ones having this index below to 0, they are mostly from cold season, so winter and spring. So being our data set much bigger than the one that actually invented this, we are proposing a modification of this index to include cold event. And that's all I have. Just to recap, we wanted to do first basin-wide waterspout climatology in the Mediterranean Sea, studying both the atmospheric forcing and the SST role in these events. And we propose a modification of the most famous index for waterspouts. And that's all. Thank you very much.
Thank you, Gloria. Next speaker is Charlotte. Yeah. So next speaker is Charlotte, and he's talking about the diurnal cycle.
Okay, I start again. Good morning, everybody. I am Salvatore Marullo, actually affiliated to the Institute of Marine Science of the National Council Research of Italy. And now I will present the work we made in the framework of the CARIT project, which is the project that has been presented yesterday by Lia, and that was supported by European Space Agency. And first of all, let me show where we are coming from for this work. The idea of the diurnal intense diurnal warming in the particular case of the Mediterranean Sea started for this paper that was published in 2008 about the frequency of very intense diurnal warming event, where we see that the Mediterranean Sea is one of the areas of the world where this kind of phenomena are very important. This starting from this, we decided to investigate the variability of the diurnal warming event in the Mediterranean Sea and the impact of this event on the heat fluxes in the Mediterranean Sea. For the Mediterranean Sea, the problem with flux is very important because as people working in this area know, there is a problem of closure of the budget of the Mediterranean Sea between the heat coming in from the Gibraltar Strait and the exchange through the atmosphere. And we found in this paper that if you neglect the diurnal cycle, you underestimate the flux between sea atmosphere of about 4 watt per square meter, which is a significant amount to consider the budget with Gibraltar. And then going on to the problem of the extreme temperature event, because of extreme temperature event are related at the same condition of the diurnal extreme event, so low wind condition and the strong insolation. We started within the CARIT project the study of heat waves in the Mediterranean Sea, in particular the marine heat events of 2022, where it was one of the most important of the last decades. And here is the paper we published on about this in the 2000. Then going more recently, there was another paper based on the global scale that produced several outputs, including the production of several data sets that describe marine wave worldwide. The first was an atlas global produced by CNR for the surface of marine wave in two versions, one without considering trend, and the second version considering trends that have been subtracted by time series before to go into the computation of the anomalies. And then there are subsurface atlas pushed by CLS in France that are also included in the data. The atlas is available at the Inframed website because also Inframed was part of the project, and they can be reached through these links directly. So I say we'll go into Mediterranean Sea, but in particular we'll try to go into a particular region or the point of Mediterranean Sea, which is the island of Lampedusa, which is a point in the center. Look at the upper left map in the center of the Mediterranean Sea, very far from everywhere, and with no strong anthropic influences. And here there is our lab where more or less everything is measured from atmospheric point of view, including atmospheric LiDAR profile, winds, budget, ration budget, and so. And here is the island. We don't see there is not so much people on this side. Okay, there is a town on the other side of the island, which is along about 10 kilometers. And this is the oceanographic buoys mooring where our measurements are taken. There we measure temperature at several depths, plus all atmospheric measurement, mean temperature of the air, water pressure, and everything you need for flux calculation. Okay, let's go on. Why this point in particular? Because we are more or less 4 questions for us. First of all, the problem of the stationary time series. If we want to compute anomalies and mean, the problem of stationary of course important. To evaluate the statistical characteristics of the anomalies, evaluate the impact of the trend and on the definition and on the evaluation. And investigate the physical project, of course, the basis of the wave progression, and quantify the propagation of diurnal cycle in depth. This is a time series. The time series is coming from this time series coming from the CMEMS data set. It's essentially based on CCI version 3 data plus other data for the beginning of the series where CCI data are not so frequent. And this is a 30-year period used for the climate computation that is from time series that of 30 years, the last year ending with 0, following the rules given by the World Meteorology Organization, which is just there is no physical reason for this choice. Okay, using this climatology, daily climatology, we can compute anomalies from 82 until a couple of months ago, let's say. and to study the distribution of the temperature near around the mean, and we see that there is on the right there is the histogram of the distribution of the anomalies with in red the fit with the normal Gaussian distribution, and here is the effect of the trending. In this case, we made the trending making a kind of single spectral analysis and excluding from the reconstruction the low frequency component, which are essentially the trends. And here again, we see that there is still this kind of Gaussianity in the distribution, which is okay. This is not a Gaussianity test, but it's a good indication of the Gaussianity of the distribution, which is interesting for the next calculation. Okay, let's go back to 2000, 2002, where the bit wave was present, the mid-NRC. This is the time series of data acquired in the buoy. The first line is the sensor at 1 meter of depth. The second line is the sensor at 2 meters, and then 5 meters, 18 meters, and 32 meters. There are several sensors at each depth that acquire data every single minute. And then here, the data are averaged over 1 hour. Here is for 2022, the time series of the data with the black line is the climatology. And interesting here to see the difference between the surface sensor and the other sensor at depth, in particular the one in purple, which is 18 meters of depth. And you see that when the warming starts, only the first sensor see the different temperature, while the sensor in depth still remain at the same temperature. This, because the two depths are uncoupled. And if you go to the other here, 2024, it is the chosen because you have more data at whole depth. Even a new one at 32 depth included the geostationary level 4 data we taken from CMEMS. And you see, okay, during wind, there is homogeneity of water from the top and to down, while again, you see the uncoupled water before doing the warming periods. And when the wind starts, mixed water, everything is mixed until a certain depth. Which depth is more clear in this other picture. In the upper left, there is a difference between the temperature at the surface and the climatology. The vertical scale for those who are far from the screen are from 0 to 4 degrees. And you see this event, there are two interruptions in the warm anomaly. One deteriorated to two very important wind events that produces the mixing. And then there is the difference between 18 meters and the surface again, and which is follow quite well the difference between the climatology and the surface. Okay, and then all the other parameters acquired, including the air temperature and the relative humidity. The interesting thing is to see that if the diurnal cycle measured at 1 meter of depth during the with the wave is not so strong, as we expect, because the condition for intense diurnal warming are more or less the same as the condition for the magnetic wave. But what happens during the magnetic wave, during the very hot period, the air is very close to the saturation, so and there is no wind, so there is no way to cool enough the water during the night, and then this decreases, at least in my opinion, the amplitude of the diurnal event, while we had two increases of diurnal warming, even just before and just after the here and here. Okay, upper left plot. And here there is the relation between mixing event, warming event, and the wind. Here, this is the square of the wind, which is more close to very proportional to the wind strength. Okay, then there is the last part about the propagation of diurnal warming, or the propagation of the diurnal cycle with depth. And if you made having such a long time series with continuous every 1 hour data, we made the opportunity to make a power spectra using the sensor at different depth, and you see that the sensor at 1 meter and 2 meters clearly show the diurnal signal. Essentially, Here. Okay, doesn't work. Okay, the 24 hours peak, while even for me that there is the peak, where I think the signal of the diurnal cycle is not present. This means that the foundational depth should be somewhere between 5 meter and 80 meter, at least in for this period. The same thing is visible also for using singular spectral analysis. This is a Monte Carlo singular spectral analysis, and see once again at 1 meter and 2 meter, you see this. Okay, this peak here, which represents the 24 hours component, which is not in this case is not visible at 5 meter depth. Okay, just to see that the concept, the idea of foundation depth that you use from satellite is something which is not trivial, of course, and you need to investigate. Last, of course, the conclusion, which is here. I will not spend so much time to read the conclusion, but I want to show you the data taken until 2 days ago in Lampedusa. And you see that here, in 2 days ago, we registered the highest temperature never measured at the mooring during the last 10 years, since when the buoy was working. And the black, I don't know. Okay. The black line represents the data for this year. You see the last in June peak of temperature, which is 1 degree over the temperature never measured in this place. In conclusion, of course, this work made a lot of several results that are still under study, and some interesting products like the atlases, the global atlas, and the highlight the importance, of course, of the data, including special level 4 stationary geostationary data, but also highlighted the importance of in-situ data and the study of physical forcing of the warming water event to go ahead with our understanding of this phenomenon. That's all for me.
Thanks, Salvador. So now into the question time. We have 10 minutes. So questions for Pia, Claudia, and Salvador, please.
Yes, I had a question for Claudia on the water sprouts. Could you clarify which GRIS data set you used to identify those and what scale they were? I don't recall if they were 10 kilometers or what scales are the features.
Okay, yeah, it's the multi-year SST product that we produce for the Copernicus Marine Service, which is GRIS compliant. It is at 0.05 degree spatial resolution, and we produce it daily as a nighttime product.
Yeah.
I have a question regarding difference between Arctic and Antarctic, differences that you showed that before. What's in what's your hypothesis about the differences because of circulation? I mean, I'm expecting that in the Antarctic region, the water circulation is much, much stronger, so it doesn't, amplify or enhance the trends or so on, or it's rather the ratio with the sea ice. I mean, that's the question I had, because we're studying how the Antarctic circumpolar current is actually a barrier or not. And from a Lagrangian perspective, it doesn't look like a barrier. So actually it acts more like a window that enables exchange of temperature. So I was curious to see if you have an hypothesis on that difference. I think.
Yeah, to be honest, I don't have a good hypothesis on that, and I'm maybe not the right person, but I would be happy to know if someone knows it. I mean, we know for the Arctic there are a lot of positive feedback mechanisms that are amplifying the warming there, but I haven't really looked much at the Antarctic region so far, so I'm not sure what it is that's causing these differences. But for the Arctic, we see the same things with the sea ice. So the surface temperatures that we produce, they are very much correlated to the sea ice. What's going on, but we see the same thing.
Yeah, isn't it obvious? I mean, why the Arctic is so totally different from the Antarctic? Because one of them is water surrounded by land, and the other one is land surrounded by water. They're completely different, and you can't melt 3 kilometers of ice off Antarctica, but you can easily melt a meter of sea ice off the Arctic. And you know, surrounded by land, so you've got a lot of warm air intrusions. So that's a lot of the source of the warming of the air is coming off the land that surrounds the Arctic basin. I've never been struck by the remarkable differences because I always thought it was obvious. Am I wrong? As a non-expert, does anybody have more insight? I think that's it. I mean, that's why we've always expected it to be much more, you know, completely different. And I think that's got to be the reason.
Yeah, I agree. They are different. So different responses, but it's interesting to see what's going on right now in the Antarctic region. I mean, if it's catching up both with the Antarctic ice sheet, but yeah, and also the sea ice. But yeah, very different responses so far, and very different regions and surroundings.
Okay, so question for Salvatore: are we looking at basically the development of the seasonal thermocline, essentially, in your data? That's what it kind of looks like. That everything's together, and then you start to get a seasonal thermocline develop, and it's driven, and the heat is kind of in the top layer, and then it gets driven down by strong wind events and starts to form. Is that how it goes? Is that what we're looking at? It sounds like it's on.
The question is about
It's on.
It's on. Okay. The question is about the behavior of thermocline with the forcing mechanism at RC interaction.
Yeah,
Or,
I mean,
yes. Frankly speaking, I have not investigated deeply this part, but I think a couple of months ago I made some tests using GOTM models for one-dimensional over this site using forcing, and we see that there is essentially thermocline go up to during summer few meters, and by winter until the bottom, which is only 70 meters where the buoy says. So we cannot see anything else than the mixing from the top to the bottom during the wind season or during particularly intense wind event, which is essentially the only way to produce the movement of the warm water from the top to down. Otherwise, consider that the warm water is in general less heavy than the cold water being down, unless you put a lot of salt in. The only physical case we found that you mix it to produce then also a variation of the mixer depth is the wind mixing.
Right. Yeah.
But nothing else.
Yeah. So in the winter time, when all the temperatures are together, that is all the way down to the 70 meters at the bottom, as far as you can tell?
Yes, at least to the 32 meters, because
yeah,
the processor is that we also had the thermistor chain, but unfortunately the bad weather conditions destroyed everything, so we cannot have anything more detailed.
Okay.
Yeah.
Don't move. So I was going to ask, I think you might have just answered the question. So there's no chance of cold water intrusions that don't reach the surface that are affecting your...
mean lateral advection.
Sorry, say that again?
You mean lateral advection. Yes, of course, there's always a possibility of an increasing of temperature due to incoming water, warm water from somewhere else, or simply because if you it's not the case here because there is not any stream of water moving around there, but if you have a current stream moving from side to the other a certain point, you can also observe an increase of temperature that is simply due to the advection of the water moving from one place to the other one. But this is not a wave coming from atmospheric forcing, local atmospheric forcing, which is essentially due to low wind and insolation. And I also take the occasion to say that insolation is not the most important ingredients, because during summer there is always sun. The variable that changes is the wind. It's the wind that drives the forcing. And we have to see what happens in the next 10 days, because in the next 10 days we expect a blocking situation in that area with, I don't know what will arrive in terms of temperature anomalies.
I've got a question for Claudia. Are the water spouts more or less a coastal feature, or is that an artifact of the fact that you're using observations to determine where they are?
You're asking me if it's a common thing that water spouts are on the coastal areas. Well, these two things. First thing, there are other water spouts, but like that also form overland, and then they form over water and they move over land, but we select just the one remaining in the water. But yeah, I think the fact that someone has to see the water spout to report it is the main reason where they are coastal. You can see very like in spotted water spouts near islands or stuff like this, but yeah, it's not because they are not forming like in non-coastal water, it's just because there is nobody there to see them.
So the only reason why I ask is that if they are predominantly a coastal feature, then you probably should be looking at a lot of the coastal weather features, like or the influence of coastal weather features, not just convection, but orographic influences on the convection, and also sea breezes, land breezes, and all of the other coastal phenomena that occur. Because, I mean, if it's just a pure temperature convection story, then it'll be more severe out to sea. There'll be more of them out to sea simply because the water's hotter when it's deeper.
Yeah. No, that's a good idea. Thank you. I will look into that.
So Claudia, since you're there, are the ones that you're looking at more fair weather water spouts, or are they tornadic?
Sorry, can you repeat it?
There are two types of water spouts.
Yes.
Fair weather water spouts and
Yes.
tornadic water spouts. Which ones are you more interested? Obviously, the tornadic ones are more dangerous, but fair weather ones are easy to see. So what's the mix that you're looking at? Which ones are you studying? Because they seem they're not exactly different, but quite different mechanisms for formation as well.
They are different, but we were looking at, we didn't discriminate between the two. So we were looking at all the ones that we have.
Okay, but I mean, so you could therefore just at least do a separation into the two different classes and then look for two different types of, sort of regimes.
Yeah, we should do that.
Okay.
Yeah, thank you.
So Claudia, I have one question. How do you co-locate your water spouts with the satellite data?
How do I collocate?
Yeah, so they are nearest pixel, or because you were SST.
Yeah, it's the nearest pixel from the position of the water spout. I understand it is not very accurate because, basically the person that report the water spouts probably put their own positions. So, but it should be, it's the best information that we have. So it's the nearest position.
Any more questions? No. Okay. So we come back 11:05. So we have about 30 minutes. Is there anything you want to announce? Okay, so we'll see you back 11:05. Please visit
at 11. At 11. Okay, we restart at 11, not 11:30. Okay, otherwise it's 1 hour break. So 25 minutes for coffee break.
Okay.
Okay?
All right.
That's it.
「村上さん聞こえますか？」
はい、聞こえます。
音声 OK です。スクリーンシェアしていただけますか？
はい。コンテンツ。どうでしょうか？
はい、画面 OK です。はい。
はい。
はい。はい、大丈夫だ。画面少しめくっていただけますか？はい、大丈夫です。はい。
はい。
じゃあ、シェア止めて、11時スタートです。
はい、11時ですね。はい、わかりました。
数分早く動いてます。
はい、わかりました。はい。
Okay. Dr. Tokat, can you hear us?
Yes, I can hear you.
Okay, we can hear you. And then, could you try to share your screen?
Yes, 1 second. Share. Okay. Can you see my screen now?
Yes.
Okay, very nice.
It's perfect.
Thank you.
Okay, thank you. Okay,
So-
stop sharing, please.
Oh, okay. Yeah. I'm gonna stop sharing now.
Okay.
1 second. Okay.
It's nice to understand the role of situation yeah, it's a massive example. And we're gonna fix the pieces.
村上さん、スクリーンのシェアを始めてください。
はい。
Hello, welcome everyone. Is the speaker in the room? Oh, online. Okay, yeah. Okay, so the next presentation is from Hiroshi Murakami on the GCOM-C SJLI observations. Over to you, Hiroshi.
Yeah, thank you. Thank you, Chair. I present about the GCOM-C SJLI observation from visible to summer infrared at 250-meter resolution. SJLI consists of the infrared scanner and the visible and near-infrared scanner, which also consists of two components of non-polarization and polarization telescopes. GCOM-C carrying SJLI has been launched on December 23, 2017, and continuing global observation for more than 8 years. This picture showing the SJLI response function of the green color area showing the response functions, and visible and the shortwave infrared and summer infrared in two channels in the summer infrared. And many channels having the resolution of 250-meter grid size resolution, including summer infrared. This is calibration structure. In the pre-launch phase, we characterize the SJLI sensor and the visible band using integration sphere, maybe, and the summer infrared. The onboard black body is characterized by the ground system. And after launch, the visible and short infrared is mainly calibrated by lunar observations following the G6 Loro model, and with the solar diffuser calibration, which is conducted every 8 days, and summer infrared, and it's which calibrated by each scan by onboard black body, and also next slide showing the example of the cross calibration with the thermal infrared sounders, and the left image is showing the channel 1, 2 by NOAA 20 Chris, and right figure showing the by the method C ESE cross calibration. So which the figure showing the good correspondence between the SGRI and Saunders observations. We confirmed accuracy using such a calibration, but mainly the operational processing is based on the blackbody calibration. And the system's temperature products is validated by in situ observation, mainly by NOAA ICAM buoys. And this is an example by the match-up result for daytime and nighttime products of SGRI. So from now, we introduced about the observations by the SGRI 250-meter or global observations. First slide showing the comparison between the resolution of geostationary satellite left figure and right figure showing the SGRI 250-meter resolution. As you see the zoom up image of the lower right figure using the 250-meter resolution, we can observe the more finer structure like white rivers and also inside inland water areas like here. And not only the final resolution, but SGRI having some reflect having the 1,400 kilometer source, which enable us to observe the both day and nighttime pair. This is a left figure showing nighttime image example, and also the 12 hours later, we can observe the daytime observation. So we can see the day and nighttime difference. And using 250-meter resolution, nighttime system temperature showing more very finer resolution image, maybe due to some cooling process in the ocean, upper ocean. The SGRI also have the visible channels which observe the ocean color. And so the 250-meter resolution enabled to clearly showing the red tide like here. And this figure shows a global average observation. Global means that 60 degrees to 60 degrees south. And by the multiple channels enabled to derive the multiple variables like shortwave radiation here, and the system temperature, this one, and chlorophyll concentration. The color showing the different sensors, the SGRI is from 2018 to now, and the other CBS models and various various GRI views or CI and so on. And this is long monthly anomaly time series. So originally the census data having some biases. So if subtract the biases by using some climatology or average of the certain term, we can derive the consistent anomaly time series like this. By using this one, for example, system temperature, we can derive the correlation between the El Nino index minus 3.7 and system temperature. You can see the correlation between the index and system temperature for big El Nino events in 1997, 2015, and 2023. And you can see the slope becoming increased from the 1997 to 2023, recent one. And spatial distribution is also observed by the global measurement. And this figure is showing the temporal linear trend from 2000 to 2025. And you can see the large linear increase in the middle latitude of the North Pacific, especially after 2020. This area increased more significantly. The lower figure showing the time series of this area average from 1996 to now. You can see the blue color MODIS, air MODIS, and red SGRI. And especially after 2020, the temperature in this area increased more faster than previous time, and about plus 2 degrees Celsius. And this picture showing the special gradient by the SIST temperature peak images of SGI, and also right figure showing the answer gradient by the answer data image. We can derive the almost same result by the both sensors. This figure showing the gradient and front location latitude is shown by the red lines. And this is made by the data from 2003 to 2005. But after 20 years, you can see the front is moving to the northward for both HDR summary flat result and microwave result like this. And this is a time series of the location latitude of the front by the HDR and also merging with the models, their models, and the answer data, right figure, the almost same result. And this is showing that 1.5 degrees latitude northward shift can be detected by this analysis. And considering the gradient of the SIST temperature was the minus 1.5 degrees per latitude. So that's correspond to the almost 2 degrees Celsius increase after 2020. We are showing the before slides. And using 250 meter resolution, we can investigate more finer areas like this is the Tokyo Bay, and upper figure showing the monthly mean of this area, this temperature, and lower is a monthly anomaly of this area. And by looking at the monthly anomaly, we can see in the average, the increase is not so clear. And the right figure showing the dotted area showing the non-significant, statistically non-significant. But by looking at the summertime, only summertime, it changed drastically. And you can see the 1.5 degrees increase per 3 years. So using the 250 meters SIST temperature enabled the analysis of change within phase. This is just example. So summary, GCMC carrying SGI has been launched December 23, 2017 and continuing more than 8 years operation. 250 meters SGI enabled to monitor SIST temperature and ocean color in coastal areas as well as lakes and large-scale rivers. And SGI data, which includes SIST temperature, ocean color, solar irradiance, etc., combined with other satellite sensors, indicate rapid environmental changes in these decades, and especially recent years after 2020, it became rapidly. And finally, SGI data are available in JAXA data portal, G portal here, address it here, and JASME's site here. That's all. Thank you very much.
Thank you, Hiroshi. We will have question at the end of the session, if you can stay.
Okay.
So next speaker is Edal.
Hello, I'm gonna share my screen.
Yeah, it's there. Okay, go on.
Hello, I'm Erdal Tokat. Today I want to present you one of my studies titled Climatology and Variability of Sea Surface Temperature in the Azores and its relation to climate indices. First of all, I want to show you the Micronesia and the Azores archipelago. In figure 1, you can see the Northeast Atlantic, and also the Micronesia region. The Azores is a part of the Micronesia region, together with Madeira, the Canary Islands, and the Cape Verde. So among the Micronesia region, the Azores is located in the northernmost part of the Micronesia region. So why we studied Azores, what is our motivation, and what is the objectives of the study? First of all, I want to present you the general circulation pattern of the study area. In figure 2A, you can see the general pattern of the circulation. So basically, Azores is located between two main current systems. On the north, the relatively cold North Atlantic current is influencing Azores on the northeastern part. And on the south, there's a two main current system, relatively warm Azore current and Azore counter current. So in figure 2B, you can see our study area and the Azore Islands. Azores includes 9 volcanic islands, and the Azore archipelago is ecologically is a very important region because it's a biodiversity hotspot. It's a key habitat for marine megafauna, seabirds, and fisheries. And for now, the sea surface temperature variability of the Azores has not been sufficiently studied. That's why to fill this gap in this study, we studied the sea surface temperature variability of the Azores. So in this study, we have two main objectives. First, we investigated sea surface temperature variability, trends, climatology for the Azores. And second, we investigated the influence of climate modes on sea surface temperature variability. So this is the data and method sections. So in this study, we used two main data sets. First, we used sea surface temperature data, and second, we used climate indices data. For sea surface temperature data, we used AVHRR Pathfinder version 5.3 data set. It's a daily data set. It's level 3, and it's with 4 kilometer resolution. It has 4 kilometer spatial resolution. The data set spans from 1982 to 2020. In this study, we only used nighttime data with quality levels 5 and 4. For the climate indices data, we used Oceanic Nilo Index, Southern Oscillation Index, and North Atlantic Oscillation Index data. So for the method, from the sea surface temperature data, we created sea surface temperature time series and climatology maps. From the data, first we created basin average monthly mean sea surface temperature time series. From these monthly mean time series, we created annual and seasonal mean SST time series, and we also created sea surface temperature anomalies. From the data, we also created climatology maps to investigate the linear trends for the Azores. We calculated linear trends from annual and seasonal time series. We also investigated the spatial distribution of the trends. So that's why we created linear trend maps. And finally, in the study, to investigate the possible connections between climate indices and sea surface temperature anomalies, we used Pearson correlation and wavelet coherence analysis between climate indices and sea surface temperature anomalies. So these are the results section. So in figure 3R, you can see the seasonal cycle for each year. So from the figure 3R, you can easily conclude that in Azores, there's a strong seasonal cycle. It characteristics in a solid seasonal cycle with minimum sea surface temperatures in March and maximum temperatures in August. To evaluate and to investigate the evolution of the sea surface temperatures relative to months, we created the second figure, which is the figure 3B. In this figure, we can see the SST evolution in relation to months and years. So if we investigate the figure in more detail, roughly before 1999, we can see more colder winters and milder summers. But roughly after 1999, the winters getting milder and the summers getting warmer. In addition to this, if you are looking at the spring and autumn months, you can see an expansion of the contours. So as a result, after 1999, the Azores is characterized by warmer summers, springs, and autumn months. So as a result, this also presents a general warming in the area. So to calculate exactly the warming trends, we calculated trends from annual time series and seasonal time series. In figure 4, you can see the annual sea surface temperatures time series for the Azores. From this time series, we calculated the trend, which is 0.027 degrees Celsius per year. In figure 5, you can also see the seasonal trends. In all seasons, the trend is also significant. Every season is showing a warming trend, with the highest warming in winter. So to compare the warming rates with literature, we found research from the Seamer et al. They also calculated linear trends for the Azore region using optimum interpolated sea surface temperature data, and they reported exactly the same warming trend as this study. But additionally, Seamer et al. Calculated linear trends for the Micronesia region. They calculated trends for Madeira and Canary Islands. So they reported that the warming rate of the Azores is approximately twice that observed in the other Micronesia regions. Another calculations that we've made is we calculated spatial trend maps. So in figure 6, you can see the linear trend map of the Azore area. So overall, the warming is significant in all Azore area. The warming is basin-wide, but when you look at the spatial distribution of the warming, you can see the warming trend is not uniform, especially on the southern part of the archipelago. The trend is more higher than the rest of the archipelago. So from the literature, we found that the study from the Franzo et al. Showed that this warming pattern, the highest trend rates on the southern, may be related to other currents and other fronts. So Franzo et al., the study of the Franzo et al. Showed that the other current and other front migrated northward during 1975 and 2005. So we concluded that this northward migration may progressively transporting warmer subtropical waters into the Azores. So this subtropical waters may partly explain the higher warming rates observed in the southern part of the study area. In this study, we also calculated seasonal climatology for the Azores. In general, there is a consistent pattern in all seasons. There is a positive north to south sea surface temperature gradient in all seasons. This means that the southern part of the region is more warmer than the rest of the archipelago in all seasons. In addition to this, in summer, in the Terceira Island, this is the Terceira Island and this is the summer, we observed a cold sea surface temperature pattern around the Terceira Island here. So we conclude that this pattern maybe showed us a upwelling signature. To better understand and resolve this upwelling signature, we created seasonal climatology for each summer month. Here you can see the June, July, and August climatologies, and if you are looking at the July, you can see that around the Terceira and also in June, July, and August, around Terceira, you can see a cold sea surface temperature pattern, which might show upwelling signature, a summer upwelling signature. In addition, on the west side of the São Miguel, we can also see a similar cold pattern. This can be also a upwelling signature.
Adal, you got a minute to finish.
I need to finish. Okay. So we also calculated correlation between climate indices and the sea surface temperature anomalies. So overall, sea surface temperature shows negative correlations with oceanic Nino index and positive correlation with southern oscillation index, and no significant correlation has been observed for North Atlantic oscillation. These seasonal correlations also show North Atlantic oscillation index show only significant correlation for winter seasons, and the ONI and SOE show highest correlation in summers. We also calculated wavelet covariance between the climate indices and sea surface temperature anomalies. So you can see some signals here. So overall, I summarized all of the findings here and finding here, and you can also find more details in this paper. So in the future, we are going to study upwelling in the Azores, marine heat waves in the Azores, and we are going to expand this study to Micronesia regions. If you are interested in these topics, I will welcome the opportunity of the collaboration. Thank you very much.
Thank you, Adal. So now questions. Yeah, please.
I was very interested in the SGLI data. It looks very useful for all the purposes you were telling us about. I have a question that's actually about the JAXA portal. SGLI data on the portal start in 2020, but in the presentation I saw data going back to 2018. So I wondered where all those years that were shown in the presentation are available.
Yes, maybe Katsu-san can answer, but the SGI data is originally from the data is 2018, but the table may be about the GRIST format data, I suppose. So
yes,
it may be from the 2020, I suppose. Katsu-san, can you follow?
Yes, you are right. And because of the data size, we only process the limited the SGL data in GRIST format. But if there is any further requirement, and we can make it. But please know that in a GRIST server, because of the 250-meter spatial resolution data is too huge, and we cannot put the all archive the higher resolution data. So the archived data is only one, I think that the 1 kilometer resolution, I believe. So, but for the 250-meter resolution data is available in near real-time basis.
Yes.
So
yes.
maybe removed in 2 months or something.
Yes.
Yeah.
Okay, thank you. I also have a scientific question. I think on the slide where you had regressed, I think it was global temperature against the El Niños, and they had different El Niños. Did I pick it up correctly that you're suggesting that the sensitivity of the global temperature to El Niño has increased over the different cycles? Did I get that right?
Yes, good point. Yeah, by making the figure, sorry.
Yes.
Correction, this figure, yes, and the x-axis is index of Niño 3.4 and vertical is SST temperature anomaly. So you can see the line is 1997, 2015, and 2025. The slope is, this number is the 1997, 0.094, and but 2023, 0.105 or something. So 1.5 times or some the slope increasing, and that is maybe relationship between the equator SIST temperature and the other area SIST temperature. Maybe something changing.
Interesting. Thank you very much.
Thank you very much.
Yes, it's a follow-on to Chris' question. I check on the portal for SGLI data, and the 250-meter resolution only covers Japan. So I guess this is a kind of volume issue. So do you have a plan to extend to other areas, or are the level 1 available at a larger scale?
Okay, I think maybe that we need to to check the resource to do that, but that depends on how much requirements coming. Yeah, because at present there is not so much people using the SGR data, and the original SGR data is available from the JAXA's G portal system in HDF5 format. But so when we make the GRIST format, it's a kind of to put the different system to making the another file. So yes, I will talk you later. But I also wanted to talk to discuss Murakami-san about that. But yes, and if there is any much request from the specific area is of the requirement, we can consider to add. But I'm not sure that all the 250-meter uploading is quite hard for us to prepare for preparation. Yeah.
The SGLI data sets are, because they're so big in GRIST format, I think it raises the question of whether in future ingest of high resolution data at, for instance, the Trishna scale of 60 meters is going to require a different way to handle the latitude longitude grids. In the level 2 data from SGLI, they use a compressed grid. So every 10th latitude and longitude is retained. So it's a sparse matrix. And that provides an enormous compression of the data files. And that's something we probably need to be considering as we make the transition into these enormous data sets, because we're going to get killed by the latitude longitude grids, which are informative, but they're ways of compressing the data.
Can comment quickly on this, because we'll talk anyway about this tomorrow, but the way of expressing the coordinates you mentioned is actually well defined in the CF convention. So there is a room to comply also to this kind of way of putting the lat long information in a lighter way.
Any other question? So I have one for Hiroshi. So you showed a validation of SGLI with IQAM voids. And my understanding that product is 1 kilometer SGLI product. So did you do similar validation with your 250 meter product?
No, the validation is using the point of spatially relatively uniform area. So we consider the 1 kilometer validation is enough for the purposes. But of course, yeah, that is also interesting. But yeah, yeah, currently, yeah, basically 1 kilometer for considering the spatial uniform area validation.
All right, thank you. So if there are no more questions, we move to GHRSST priorities discussion for the session. Yeah, please.
So I'm going to come back to SGLI data. I think this is really interesting. I understand that it's not been so much used, and I can maybe understand that in the global sense, it's not so different to some other sensors, but this 250 meter thing for the coastal zone and with the UHR coming up, I think is something we need to be more awake to within this community. Now, I understand that the mission can, in principle, technically could last until 2030, but the situation that Masako, you explained to us for AMSR 3 is also relevant to SGLI. So it's not guaranteed that this 250 meter data will be available as long as the mission could technically run in terms of fuel and so on. So I think if there are people in the room who want to start looking at this seriously, then we might have grounds on which to have an opinion on that possibility as well. But we would need to show that the community is really interested in using the data in a serious way to make a serious argument. So certainly, I'm thinking about lake. We work in lake surface temperature as well, and it seems to be very relevant there. I think we would need to look at the level 1B probably for our purposes for that. But there might be other people who are very interested also in the already processed to SST data that are in the room. So we'll come back to that, I'm sure.
Yeah, thank you very much. That is very welcome comment for us. Yeah, I hope we continue more years until the hardware limitation. Thank you very much for your comment.
Anything else? Yeah.
Thanks. I wanted to maybe ask the people here in the room to think or maybe express how they understand. Now we have this combined sea surface temperature and sea ice surface temperature product, and looking at marine heat waves when it's the Arctic, so it's maybe over ice. And also listening about marine heat waves in the tropics, about coral bleaching. Do you feel there's a confusion there? Do you think we need different terms? How should there be a one name for independent of where it's happening? Yeah, feedback, ideas. How do you think about it? Does it shock you when you hear marine heat waves in the Arctic? when there's no direct maybe relation to the water underneath, or yeah, just brainstorm if you want. Thanks.
Hi, thank you for bringing that up. Me as studying the meteorology, the meteorological community has also done some advances before the oceanographers on heat waves, on atmospheric heat waves. And I think there is a paper, cannot remember the name now, but there is a paper suggesting that we differentiate the term marine heat wave for the extreme internal variability of the system and the marine stress, which is related to the global warming. So to separate that, the internal variability event from what the warming trend is telling us, is what that paper was suggesting, just for not confusing more of the community outside the scientists. I think it's a great discussion to have.
I think that heat waves exist in atmosphere, land, and ocean. Okay, so the name to change the name perhaps can be a mistake for us. Okay, so I think it's better to maintain the name as it is. But perhaps what we should go as a step forward is also to identify, link the single event to the main forcing. That's a different. So we could also call extreme heating of the ocean or extreme, but perhaps this could be a disadvantage for us, since all the, first of all, before a new name pass to the community, it takes time, okay? And second, it's important to understand that there is other community working the same problem issue. So I think it will be better to maintain the marine heat wave as name.
I was not suggesting to change the term marine heat wave for the known areas where there is full water from the top to the bottom. No, I was just wondering if hearing about marine heat waves in the Arctic, especially over sea ice, where there's, there's sea ice, then it melts a bit on top, so there is a heating, and then there is the sea ice, and then there's the water below. So what happens at the top doesn't necessarily go down to the water. If that creates a confusion, I'm wondering if that can be a problem. So it's up for, I'm not saying we should change the marine heat waves name, just to clarify.
Can I just add to what Jonas said? So it's a more matter of if we should use another name for what's going on in the Arctic, if we can use marine.
I understood perfectly what you are saying, but the only things that I was highlight that heat waves there is also over land, and you consider that the ice is similar, not like land, but is similar. If perhaps you can identify, say we have a heat wave over ice, okay? But the concept of heat wave, I think, is more general, and we are going towards integrated observation phenomenon in Earth system. So change the name, I think, is not. But to add to the phenomena, the different contribution that force in the process could be important, I think.
I don't think it's a GHRSST priority to have an argument about nomenclature. Having said that, I do agree that on ice, it's more like the land. And that means you shouldn't use the Hobway definition, because over land, a heat wave is defined above a fixed temperature. That's how meteorological agencies define heat waves. It's not relevant, not relative to the annual cycle. So there's a problem there, but I don't think it's a priority for us to solve.
Just a small comment about the terminology of marine wave for the specific case of the ocean. Maybe we just need instead to change the name. Okay, I agree for the problem for the ice. Just revise the update definition because there is a threshold percentage to take into account a minimum length of 5 days. Maybe we have to also add a maximum length of the period because if it becomes too long, it falls into the problem of global change of low variability.
There is another micro here. You can stand up and I don't know. What if it's
I want to start a different topic, if that.
Perfect.
Okay. So my impression from conference so far, or from previous GHRSST meetings, I feel that it's very heavily satellite product focused. So we are producers, we are users, but I feel like in-situ observations are not getting enough attention. And we don't have a lot of people particularly working on in-situ or giving, I think the Bureau of Meteorology, we give annual updates on the in-situ observations. But I could be wrong, but I didn't get that impression from many other agency reports. And I mean, we do have regular updates from, for example, Gary Collins on the trusted buoys. We have Ship for SST project. But, you know, when I was collecting in-situ observations over the Southern Ocean, I realized, hey, we don't have a lot of very good data, especially Southern Ocean. It's basically a data desert. We all know that. So I was wondering what the community thinks of. Should we prioritize a bit higher of the in-situ observations? Because everybody use that, you know, we all know how important they are. And especially, you know, with the AI and data-driven technology coming, and it's gonna change everything. In-situ observations as ground truths will be more important. I'm not satellite data awesome. I love those, but I'm just saying, what about the in-situ observations?
So the way GHRSST handles that is that we do that in cooperation with the other institutes that. So, for example, we've had a long relationship with the Data Boy Cooperation Panel, and you mentioned other projects, but the Trusted program, for example, came out of that cooperation. We've also interacted in the past with the Argo operators and so on. And yes, we're very happy to identify our needs for in-situ data and then to work with those other organizations and represent the needs of this community to in-situ networks. So if you've got specific in-situ requirements and so on, for the purpose of satellite SSTs and high-resolution SSTs, that's absolutely in scope to raise those. But we're not solving those problems as a community in this meeting. Yeah.
I wanted to make a comment real quickly.
Can I add
Sorry.
a point on this?
Can I make my comment first,
Yeah.
please?
Okay.
So I think his point is a very good point, and I do recall in GHRSST that we started putting those kinds of information in our agency reports at some point, and it's kind of fallen out. So I think it is a reasonable question as to what in-situ data sets our agencies promoting and using. And it could be an item that we bring back into our agency reports to make sure we're reporting out on that as part of this group.
I come to your position because I think we have a particular issue at the present moment from in situ observation. There is a strong request to maintain one Argo program. I think we should come from here also the request to maintain the drifting program, and this should become from this community. Europe is launching the Ocean Eye, and in Ocean Eye will try to maintain the system. They are thinking only to Argo. Argo is crucial in measurements for the ocean part, but I think for this community also the drifting program is very, very important. So perhaps something from here should come in this sense.
Yes, I think it would be useful to have, where agency reports have an insight onto in situ program, absolutely, it would be useful to reinstate those as routine, because we need to be informed about the network to understand what's going on. And Leah's just mentioned some current issues. Yeah, so we should make a note on that for future agency reports to remember that. So thanks for raising the topic.
Just very particularly, is IQOM still going on, or it stopped last year? IQOM. But the web page is not updating up after May 2025.
I think, yeah, a lot of people are wondering about the data are in there. The web page is not being maintained, but we do have a person now that we were able to bring back, and we should be working on that as on the order of months, and continue with the quality control and getting things back under control. We recognize how important a resource it is, and I'm sorry for the interruption, but we're working to get back on schedule with that. So maybe on the order of months, less than a year. If you're looking for anything particular or have trouble getting something, email someone here at NOAA and we'll figure it out if the website is holding you back.
Oh, okay. Okay. Yeah. Okay. So I go back to satellite SST. So we talked about many CDRs today. So if we put in our users' shoes, then there are many CDR now available for them. And what we are talking about, the complexity of the terms, there is a complexity of which product to use also. So I think if we were providing the uniform uncertainty information with each CDR, that would be. So with the CDR, there is a lots of options available for the users. So if they were getting uniform information on the uncertainty coming with that CDR, that would be most useful for users.
I think that will be a topic of discussion tomorrow. So we'll have another priority session to address that one. I think it's a good point.
All right. If we don't have anything else, we will stop here. And there is a group photo. Yeah, so over to Christina.
Yeah, before the photo, I just want to make two brief reminders or announcements. You have received this morning the information how to vote for the re-election of the science team members and the nomination of the new science team members. So please vote today and tomorrow so that we can announce the results on Friday. Sorry for the short notice, but we are all here. So I just hope you find some minutes to do that. That's the first thing. And the other is that I think we just uploaded the list with the contact details of all the attendees. So if you need to contact anyone in the room or in the meeting, you can just find that in the Moodle, okay? And this is all from GPO. I don't know if the local organizers, I don't know where is the photo, how do we deal? Do you want to give instructions?
Okay, we will take the group photo. It will be the entrance, outside of the entrance, and the photo will be taken from the second floor. So you need to look at the window in the second floor. So please go, and you can leave the luggage in here if you will go to the excursion tour. But because the excursion tour, as Ellie told yesterday, we will depart this here in 10 minutes.